it's my honor to introduce our keynote panel. Our keynote speakers really exemplify this year's conference theme of affordable energy. They're going to share with you how buildings can move from being a leading source of carbon emissions to a sink. They will share how the value and cost of decarbonizing our buildings is real. They'll talk about the relationships between energy, materials choices, and climate. And they'll talk about climate justice and social equity. So I'll briefly introduce our three speakers, and you can find their full bios in the program if you're interested in learning more. First, Chris Magwood is Executive Director of the Endeavour Centre in Ontario. McArleton is the founder of New Frameworks Design Build in Burlington. And Jacob Racusin is co-owner of New Frameworks, and both are also leaders at Yestermorrow Design Build School. So please join me in welcoming Chris, Ace, and Jacob for the keynote.
Thank you. Hello, everyone. Good morning.
Oh, great. Perfect.
We almost never sit down, so we're just going to push them to the back. We might use them a little bit. Welcome, everyone. Thank you so much, Rebecca, for that introduction, and really glad to be here with all of you at this really critical conference that I think galvanizes so many of us in our work. So Carbon Drawdown Now is our talk this morning. We are going to be talking about how all of our work in design, build, and development, any policy, any place that any of us sit, are able to achieve this critical climate action with our work. Oh, thank you. I was like, where's the clicker? There we go. Great. So we're going to start off with Greta Thunberg. I think many people in this room recognize Greta Thunberg. She is well known for being a 15-year-old who also happens to be neurodiverse on the autism spectrum. And she is an incredible force, along with many other youth globally, who are calling to us to say, there is no time anymore. We all thought, it's okay, we can work on this, we can figure this out, we've got to get to this next place before we can do the right thing. We very purposefully did not title this talk this morning, Understanding Embodied Carbon in Our Buildings, right? We didn't title it, let's think about this. We very clearly said we need to take action, and that is what this is about. So you'll see we're going to kind of work on two levels in this presentation. We're going to have sort of a simple kind of point, and then also something that addresses more of a systems level thinking kind of throughout the presentation. So this format will show up a few times. The simple goal that we're going to really just present to everyone this morning, and we're going to charge the Vermont and community beyond Vermont with this goal. We want to create a new normal. We must create a new normal. And that new normal is to create zero carbon and carbon storing buildings for everyone. And the second part of that is to address both the climate and the social crises that we're facing. It's funny to name them separately because I think at this point, many of us recognize, and we must recognize, that those are interconnected. So the systems goal, which is connected to that first one, but is a critical part to actually achieve what we're going to do, this radical change that we're looking for and that we need, is that in order to address this crisis, we have to change not only our thinking from being within our silos, from saying, I'm a builder, I don't need to understand regenerative agriculture, I'm an architect, I don't need to think about immigration. Those things, we cannot afford that any longer, even if we could at one point, which we could probably argue about whether we ever could have afforded that. But I think at this point, the interconnected nature of these crises that we're facing require interconnected and systems thinking to address them.
So the simple problem that we're all trying to address is there's an overload of carbon dioxide in the atmosphere, right? All this focus around reducing the atmospheric loading of carbon dioxide. We're at 415 ppm, parts per million, and climbing. The target for stabilizing our planetary ecosystem is somewhere around 350. So clearly, that is the problem that needs to get addressed. But it is really important for us to own that that is not the only problem, nor is that actually the root of this panoply of different social and ecological problems that our planet faces. An extractive fossil fuel economy is a root cause to a host of different sufferings across our planet, from human health impacts, mass extinction, biodiversity loss, racism and classism, and also a host of different social inequities. We need to get to the root of the problem to be able to develop the sustainable future that we're actually trying to create, and identifying that an imbalance in atmospheric chemistry is part of what's pushing us forward towards action.
So when we think about this on the buildings level, try to bring it to what everybody in this room is really good at, the simple solution is that the carbon emissions from the buildings that we all design, make, work on, renovate need to come down, and they need to come down sort of at the rate that the IPCC is saying is necessary to avoid the worst of climate change. But the system solution means that the simplest steps we can take, and we're definitely going to show you a whole bunch of simple steps that are really impactful, but the simple steps like material substitutions aren't going to get us that whole way. They're not going to fix the system. They're going to be a small part of the solution, but that we have to think about, as Ace was saying, how all of this, how what we're doing in our sphere connects to all of these other spheres. How does it connect to forestry? How does it connect to agriculture? How does it connect to affordable housing? All of these other issues. That becomes part of our domain if we're working on this.
So just to start off, we're going to do a teeny bit of earth science and understand exactly what we're speaking about. Because like we were saying, in order to get to how our solutions are going to be effective, we have to understand the systemic problem. So how many folks in here know the carbon cycle or remember it from school? Yeah, it's like kind of a smattering. I don't know. I'm always surprised about that. Because the reason that we're able to live right now is because of the carbon cycle, and also the nitrogen cycle, and also the water cycle. So those three cycles that exist on our planet and on all the different parts of our planet. Is this animated so the things come up, or are they just gone? Okay. Anyway, what we're looking at here is the different parts of the planet that essentially interrelate with one another and either hold carbon for a certain amount of time and then exchange it between itself and another one of the spheres. So I'm just going to use this pointer over here. This big blue chunk is our oceanic, oh there it is, thank you, our hydrosphere. And that's lakes, oceans, also water vapor in the atmosphere. And then we've got the geologic, down here, the geosphere, and then that's rocks, basically, and the lithosphere, anything below the soil. And then we have the pedosphere on the right, that's the soil that represents the exchange between the rocks underneath and the atmosphere, the biosphere of living creatures, and the water as well. So essentially, so the biosphere just popped up there. The percentages there are the percentages that exist globally of those spaces, and the carbon moves in and out in different forms between all of those. So that's critical for us to understand, and I think really briefly I'm just going to say, Jacob mentioned greenhouse gases, and the percentage parts per million is an issue for climate change. The planet Venus, many people may be familiar. It's a fan in our solar system. Venus is a lot hotter than Mercury, which is one planet closer, and there's one reason to the sun, and there is a key reason for that, and that is that Venus has an incredible concentration of carbon dioxide in its atmosphere, which creates a very intense greenhouse gas effect. So because all of the carbon in that planetary system is in the atmosphere, it is a very heated, you cannot exist on the surface of the planet. So our planet is habitable because we have a carbon balance. So that is the key point that we should all here understand. So the fact that carbon system is out of balance, which is currently what is happening with climate change, is why we're in trouble and why we need to change course. So you can see here we've got emissions activity due to human activity. I just want to be clear, carbon is always moving into the atmosphere. The fact that it's moving into the atmosphere is not a problem. but the fact that it's moving more than it should out of balance by human activity is the point that we need to pay attention to. So we've got land use changes, which is a huge thing. It affects soil and allows carbon to move from soil storage into the atmosphere. And then we've got the pulling up of fossil carbon and fossil fuels and burning them. Those two activities that we've been doing are outbalancing the system, putting way too much carbon dioxide into the atmosphere, and all of the subsequent problems that we are seeing with that. So I guess actually I'm going to back up just one second. On the prior slide, here on the right, you can see the photosynthesis line coming down to the plants here. So this is super key. Everyone again, photosynthesis, hopefully grade school at some point. And as a reminder, what we're doing with photosynthesis, plants take sun energy, water, and atmospheric carbon, and they make glucose and oxygen, two things that we really want, food and oxygen. So in that process, they are storing carbon into the bodies of the plants themselves. So you can see here the plant shoots represent about 30 to 50% of the carbon content that the plant stores. And the plant roots, which you can see beneath the soil, generate about 1 to 3 times that through an interaction with fungus in the soil and create soil storage carbon or soil organic matter, which is where carbon lives in the soil. So this is critical for us to understand because this is a part of what ecologists and folks understand as the short carbon cycle. So there are 2 carbon cycles. One works with the lithosphere, I love saying that word, lithosphere, rocks in the geosphere, and that takes eons, 100 million years. The short carbon cycle is something we can affect directly, us in partnership with plants. And so that's what we're going to be talking about today. So this positive intervention that we're advocating for, that we're asking everyone to put into practice, is that we need to stop moving carbon from fossil fuels into the atmosphere. So we know that. We have to reduce emissions. We're not standing up here saying that we can keep burning stuff as long as we store it. No, we also have to stop burning stuff. And we have to stop land use practices that cause that as well. And we have to move the carbon that is in the atmosphere back into the biosphere. So we are going to take atmospheric carbon with the use of plants, partner with them in respect, and put them into our buildings to create buildings as the 6th carbon sink. That is something that we as humans can do. So we're going to speak for a second about soil because it's actually really huge. Soil is a connector that, as I mentioned before, connects the geosphere with the biosphere. It's kind of the transition zone between those two things. So it is a mixture of inorganic and organic compounds that store quite a bit of carbon for us globally. So the key piece that we need to understand is that when we are using carbon storing materials, plant-based materials in our buildings, if we do not pay attention to the way in which that is done, we will actually create more problems. So for us, we'd like to charge everyone here that the success of a building can be measured by how much soil was built in the process of those resources that were used for the building, for them being created. So this is a good, quick kind of look at what we're saying very simply. So on the left, you see the removal of atmospheric carbon during the growth of plants. Carbon drawdown, that's already happening every day right now without us doing anything. That's happening. The second part is our human engagement, how we're engaging with that. And so those are where the carbon emissions come in from manufacturing and harvesting. And we're going to talk about that today as embodied carbon. So what we're proposing is that the net sum of those two things needs to be negative. It needs to be a storage number. So that's that net carbon storage that you see on the right going down through the buildings. So between our engagement with natural systems, net carbon storage. But we have to actually go a little bit further than that. That's a great place to start. And then beyond that, we need to say, Okay, but what about the soil? How much did we build that soil in that process? How many trees and plants and forests did we protect with biodiversity and regenerative agriculture in the process of supporting that natural CO2 drawdown that plants provide us with? And then, in addition to that, to the right, you see the emissions from manufacturing and harvesting. It's a little maybe difficult to see, but this is a windmill that's providing energy to that factory. We've got solar panels providing energy to that factory, and we have a little, can anybody see the plug popping out the back of that tractor? So we're looking at changing on a multiple scales the way that we practice harvesting materials from the earth that we depend on, building buildings. If we pay attention to how that's done at every level, we magnify, we catapult, we radically multiply the benefits of our action. So you can see that net carbon storage is now big green bubble. The drawdown is a bigger, very light bubble. Yeah. So the last thing that I want to say on this is I would encourage everyone to get this book if you have not yet read it. It's Farming While Black by Leah Penniman. She is a farmer in New York State and runs a project called Soul Fire Farm. And Leah has a really great quote that I think is worth us considering. She says, "Organic matter in soils on the plains plummeted by 50% in just one generation of white settler colonialism. I realized that all of our efforts to heal the soil entailed the restoration of organic matter and was, in effect, a decolonization of the soil. We were inviting our non-human relations back onto the land and back into relationship with us." So for us, what this really points to is that when we think about what does colonize mean? Colonize means that a force, an action, a group of people says, I'm going to go and I'm going to seize this piece of land or this group of people or this resource, and I'm going to do whatever I want with it, irregardless of what was there before, what it is, what its nature is, any of it. So that sort of violent and sort of power-grabbing aspect is something that really minimizes the benefits of biodiversity and the natural balance that exists in nature. So for us, carbon action and paying attention to the way in which, not just carbon gives us a window to this entire complex system that we are a part of, and how we can be a part of it in a beneficial way, in a positive interrelationship that is respectful, rather than one that is extractive. So the very short other thing I'll say is that in Project Drawdown, which many of you, if you have not looked it up, please do. Project Drawdown, number 39 on their list, is supporting indigenous land use management. Indigenous people manage 18% of the land globally. And on those pieces of land, there is significant less deforestation, soil carbon loss, and significant storage of carbon on those lands. So another thing that we can do to take action is to support indigenous land management and indigenous land management practices. So I think that, again, we're speaking here the difference between colonialism and indigenous practices, which is a key part of moving forward.
All right, so this is going to be maybe familiar to many of us in this room that are sort of aware of the scale of the impact that our industry has on global carbon emissions. So we know that, some recent data is showing around globally about 28% of global carbon emissions comes from the operation of our buildings. And this is the whole point of the energy efficiency movement, right? Is to draw that, is to reduce that impact through efficiency measures. But we also see there's an additional 21% of global emissions as a result of creating all the materials that it takes to make these buildings happen in the first place. And where we are right now with the chemical imbalance in the atmosphere and the scale of impact of our industry is that we simply cannot, which is this top one for, we cannot ignore those two pie wedges. That 21% has to be part of the place of intervention that we take as an industry to minimize our impact. So let's look at the life cycle of a building here. We're starting with raw material extraction and processing, goes through manufacturing. All those materials get onto a site. They get constructed in the whole process of construction of creating that building. And then there's the operational phase. That's the one we've been paying a whole lot of attention to. There's, maintenance and repair, the demolition of the building, and then recycling or disposal of all those materials. So there's an entire cycle that our life cycle our buildings go through, and there are emissions that occur on every single stage of that cycle. So the majority of our focus as an industry up until this point has been on the operational use. And that is critical because it is that biggest wedge of the pie. So fundamental that we have been paying attention to that, and give tremendous credit to everyone in this room and this entire community of Efficiency Vermont specifically, and the broader movement of better building energy efficiency practitioners. We can take a tremendous amount of pride in the efforts that we have done up to this point in reducing this this largest and most critical impact category. And so we need to keep that effort strong. In no part of our message in broadening our scope and our focus on other points of impact do we in any way mean to diminish the impact of that work or the critical nature to amplify and increase the amount of operational emissions that we are reducing in our practice. And also, we need to broaden our view beyond simply the operational phase of the whole building life cycle. And so we've been speaking for a very long time around energy, and when we're referring to a lot of our goals and targets and language around the efforts, it's around energy efficiency and energy reduction. But we're not talking, the atmosphere is less interested in how much energy we're using and more interested in the carbon emissions as a result of that energy production. So to get a really good understanding of what the true climate impact is of our building's operational energy use is to not just look at the energy consumption, but the associated carbon emissions. So when you look at how much energy we're using, and then we look at the emissions factors from that energy source, be it fuel oil or natural gas or electricity, that multiplier then results in our total carbon emissions from operational energy. But what we know is a net zero energy building doesn't necessarily have net zero carbon emissions. How you do that calculus, and then of course when you look beyond just the operational use, there is much greater impact to the atmosphere and our emissions profile beyond simply how much energy we are using and how much we are offsetting with solar panels. And so what we're inviting into our scope of reference for the sake of this conversation right now are these this first part of the building's life cycle. And we're looking at everything from extracting those materials or harvesting those materials from the earth, all the way through to the point that the building gets built. And we're looking at, that's what we are calling upfront embodied carbon emissions. When we talk about embodied carbon or embodied emissions, we're looking at all of the that result from the full life cycle of that building's life cycle. When we talk about upfront emissions, we're looking at that category of the life cycle that's happening before the building is even in operation, before day one of occupation. And that whole bank of emissions in those first parts of the cycle are the upfront emissions. And so we can see there's a tremendous amount of impact that comes in each one of those phases. And just to make sure our definitions are clear, that upfront embodied carbon is what we're talking about when we're looking at the material impacts of our buildings. And the reason we're focusing so specifically on that part of the life cycle is because we have very, very little time to reduce the emissions of our industry. And while we have an entire, multiple generations ahead of us, if we play our cards right and make the changes that we need to. And those end-of-life cycle emissions also count. The point of intervention is right now. And so the first part of that time cycle, of that life cycle, that is the most critical place of intervention when we consider the short, very narrow window of time we have to make meaningful reductions. So looking at this graph here, just to explain what's happening here. There we go. So day zero, we have a whole whack of carbon emissions that has been invested into the creation of that building. And then every year, we have an incremental addition of operational carbon emissions. And by a certain point, those carbon emissions come from the operational use of the building outpace the initial investment of emissions that we used in the production of those materials and the construction of that building. But we are starting into the lifespan of that building with an incredible carbon debt if we're not paying attention to the impact of those materials. So there is not a way to net zero energy our way out of that problem when we have already invested decades worth of operational emissions just in the construction of the building. So if we're truly trying to get to a goal of net zero carbon by 2050, we cannot do that through energy efficiency measures alone. They are critical. We have to keep that bar high, but we cannot ignore all those upfront emissions that we have invested into the building before the building is even occupied. And so linking that back into the context of the full global carbon cycle, we can see that the potential of our buildings in business as usual practices will continue this cycle of imbalance if we're not attending to the impacts of the materiality and the construction practices of our industry. But if we can intentionally intervene in that cycle and encourage carbon drawdowns cycles that exist within our natural ecosystems, then we have the potential to reverse that impact.
Okay. This is the part that we, of the talk that we called last night, the nerdy graph slides.
Nerdy graph part.
Yeah. So this is where we'll sort of dig into, what does this look like at the building level. And so this is based on a study I did over the last couple of years where I took a sample single-family home and a sample multi-unit building, and I found data on all the materials you could possibly use to build that building, and I kind of clumped those materials into ones that had really high upfront embodied carbon, kind of like mid-range, or I called typical, the absolute best things that you could go get off the shelf today, and then the absolute best practice that we could find anywhere, and sort of tallied up what the emissions were for those buildings in all those scenarios. All of this data comes from these documents called environmental product declarations. This is something that more and more companies are doing. Couldn't have done this study 5 years ago because there weren't enough of these around, but now there's enough of them that it gives us a really good baseline. I could sort of look at examples of these for all the materials that we would normally use. And so all of these are done, they're third-party verified studies that companies commission, and one of the data points that comes out of them is the global warming potential of the materials, and that's what we've used in this study. So what I'm going to do, and I'm not going to sort of linger and talk about each of the assemblies and materials, you can sort of read them as they go up, but what I want to do is give you the sense that I basically figured out, okay, how much of each of these materials was in this building, and I multiplied it by the global warming potential factor and added it all up. This is as though, this is the larger building, the multi-unit building, so it's 10,000 square feet, 4-story, 8-unit apartment building. And basically it's built in this version to, I'm from Ontario, so to the Ontario Building Code minimum standards for energy efficiency. So if I chose materials from the higher end of the spectrum, that building has over 200 tons of emissions associated just with making the building in the first place. So that's the carbon debt that Jacob was talking about. So whether I make this building super energy efficient or net zero, or no matter what I do, this building sort of has a 200 plus ton kind of carbon debt that it's caused on the planet before anybody moves in. So then I subbed out that first round of materials for more typical materials. These are all pretty much straight substitutions. Both of these examples, you will recognize all these materials. We all use them. So without taking any huge steps, without making any big change to the practice at all, that same building can now come down to 68 tons of upfront carbon emissions. Super big impact, super minimal effort or steps needed on our behalf to make that difference. And that's a huge step. to be able to affect that much change simply through some material substitution. So the next model I did, I thought, well, what if I really was being intentional about this, and I am a builder, so I care about this, and I want to do this with the things that I can go get locally that are code compliant. I don't want to veer off into, you know, alternatives or anything. What could I do? What would be best practice? And so this one starts to go up, and then all of a sudden I run into, in this whole study, my first negative number. And so now we're talking about the carbon storage, the carbon drawdown that we were first referring to in the opening of the presentation. And Ace will tell you what that's all about.
Awesome. Yeah, so, right. So as Chris said, I think you had a moment of just kind of being like, wait, what? Did I do the math wrong? Why is there a minus here?
On this?
Right.
Yeah.
So again, this is, you know, like we were talking about here, as builders, and as a builder doing your own research, you were leveraging this plant-based storage as an insulation material to help the total impact of your building. Right, so then, like we were showing before, that little equation of, you know, natural systems plus our activity equaling captured carbon. So really this is kind of the nexus of what we want to explore with you today, is creating this whole new paradigm of building materials that actually remove and then store that carbon in the building. So as long as those materials do not rot or burn, we're good. And I think most of us here have worked for a long time on how to not have our buildings rot. So hopefully we're good on that one. Great. And so then, yeah, many options exist for this. So I know it might seem like, come on, are you guys trying to sell us on, you know, some crazy, you know, technology that isn't yet accepted by code or isn't practical to achieve or buy? And the fact is that some of these are actually very achievable and accessible, as Chris was mentioning. Cellulose is a great example. I think many of us in this room have used cellulose in either dense pack or loose fill forms in multiple places in our assemblies. And another kind of very accessible one is wood, which can be complicated because wood, as we sort of remembering from before when we were talking in the introduction about the way in which the wood is harvested is actually very critical to whether or not it has a good net storage at the end. So there are complications there, but sustainable timber is a really great resource for storage that we can all support. Especially here in Vermont, we have a lot of sustainably managed woodlots that many of our rural foresters and sawyers are managing, and that's something that I know our company takes a lot of advantage of, using local wood wherever we can. And then wood fiberboard is another one that has really, like, in the last few years, catapulted in terms of visibility. So I recommend that everybody check that out. It can be a really good swap, one-for-one, for rigid foam in multiple locations in the building. So those are some that are just like, right now, you could all like take a look and find those. Some of these other ones are more medium. The three of us have had a long history in straw bale construction. So there are plenty of new innovations happening with straw bale that are really worth looking at. Our company built panels, a panelized wall system out of straw bales for a project recently. And that's something that's been happening in Europe a lot, and that I can see North America really starting to get into for solutions for, you know, multi-unit and single unit buildings. And then some of these are a bit more R&D, but I really encourage everyone to pay attention to a lot of these developments, because there's a lot of exciting innovation happening around carbon storing materials in buildings. So I think we're going to see a lot more, you know, as we move forward.
Okay, so we'll kind of continue the narrative of this yellow type building that has its first negative number. So that's from the wall assembly that has dense packed cellulose as the cavity insulation and wood fiberboard as an exterior insulation. Now we've got some FSC certified cladding that drives the number down further. We've got some FSC wood on the interior walls. The windows drive it up a little bit. So you can see it's going to go up and down depending on what the sort of materials are. But the amazing part is this building comes out to be a net storer of carbon. So without, with very little in the way of deviating from our sort of like typical practices, from our norms, we can go from making a building that has a couple hundred tons of emissions associated with it to one that's actually below the zero line, that's actually starting in a place where it has stored more carbon than was emitted in making it. And then the final one that I looked at was, well, what if we took the absolute best materials, and it doesn't matter if they're common practice, and it doesn't matter if I can get them at Home Depot, but they're out there and people use them, and they're things that we could feasibly use, and actually in our practice we do use. What if we use the best possible scenario? And you can see most of these numbers are going on the downward slope, and that same building can now store 117 tons of carbon up front. So now we've almost flipped the paradigm of the first two buildings completely upside down, and we've now got a building that's storing a really quite vast amount of carbon from the get-go. So you're actually drawing down. That's the carbon drawdown we're talking about. That's a drawdown building where there's a significant amount of carbon came out of the atmosphere and is stored in the building. So that's if I modeled that building to Ontario Code minimum standards. I also modeled it as though it met our upcoming 2030 net zero codes. And what's interesting here is that in increasing the energy efficiency with the first two models, the red and the blue typology, in order to get some energy efficiency and to try to make an impact on emissions on the operational side, we've actually driven the emissions up by adding insulation that has a carbon footprint. And the exact opposite happens with the other ones. If you're using carbon storing insulation, by adding more insulation, you're adding more storage. You've kind of started with a win-win. So instead of kind of making this carbon investment and hoping it pays off, you're just doing a better thing from the beginning and then continuing to do the better thing afterwards. So it's not that more insulation or more or less energy efficient is better or worse. It has a lot to do with what materials you use to get there. And so that's sort of a look at those materials, those assemblies. And here we've sort of changed the numbers over to kilograms of CO2 per square meter of building area so that it's easy to kind of compare between buildings. So the first numbers were totals, and this is what those totals look like expressed over the size of the building. What's interesting, like that might look like a number, and you're not sure what that number means. But if all the buildings that are built in the US in a year at that scale, so from sort of 4-story residential down to one single unit residential, so 240 million square meters a year, if they're all built in that sort of red typology way, that's the equivalent of contributing the emissions of 15 coal-fired power plants a year from making residential buildings in this country. That's a big impact when it's spread out. But on the other side, if we're able to sort of do best practice and really make these buildings carbon storing, first of all, you've eliminated the emissions of those 15 coal plants, and you're storing the equivalent of another 10 coal plants worth of emissions. So this is, if you're thinking about, oh, I could do this on my building, but does my building really make a difference, and how big a deal could this be? If we can actually get this industry to move from what it looks like on that red bar to what it looks like on the green bar, that will be the single biggest emissions intervention that's happened on the planet. When my province of Ontario shut down our 6 coal plants a few years ago, that was the biggest drop in emissions in North America, and we're talking that the building industry could almost double that on an annual basis. So the potential at scale is really large.
And I think what's really huge about that, Chris, too, is that that's each of us individually in our little projects, and there's something really empowering about that. We're not just talking about big cities that have high-rise buildings with multiple architecture firms collaborate. Like we're saying all of us in our projects that we do every year, and there's something very democratic and empowering about that I think we all need to really ground in with.
Yeah. And so just the other question that comes up when we talk about this is, okay, that sounds great, but do we even have enough of these kinds of materials to be able to do this with? And the answer is yes. So just just grain straw right now, so not looking at all the other biogenic materials that we looked at in those buildings, but just grain straw, over 2 billion tons of that gets grown on the planet every year. We eat the seeds off the top and the stems are left behind. We can use those stems in all kinds of ways in our buildings, and people do. But that amount of grain straw alone is enough to store all the transportation emissions that we produce on the planet. So in other words, that drawdown is already happening. The farmers plant enough wheat, oats, barley, rice, rye, all of those kinds of things. Those plants grow. They are literally already taking all of our transportation emissions out of the atmosphere and putting them in the plants. And all we're missing is that we typically burn off those stalks or let them rot or in some other way put the carbon back into the atmosphere. If we can just figure out how to get it from the field into a building, then that's a massive amount of potential drawdown.
I want to take a quick minute just to make sure we're really clear on definitions of terms, because I realize we've been throwing on carbon, carbon dioxide, greenhouse gas emissions. So just to get super clear on the definitions, when we were talking about carbon emissions, that's actually a bit of a shorthand language. We really mean carbon dioxide. But carbon dioxide is not the only greenhouse gas that gets emitted through our building practices. Refrigerants, blowing agents, there's a host of other chemicals that have thousands of times the impact of a single molecule of carbon dioxide as a greenhouse gas. So to be able to make all of those different greenhouse gases equivalent to a common metric, we use carbon dioxide as the common equivalency. So anytime you see CO2e, that's carbon dioxide equivalent, and it's all the greenhouse gases sort of normalized to the value of one molecule of carbon dioxide. And then when we're talking about carbon in terms of carbon storage, that is actually elemental carbon, the C, that's being bound up in the plant. And so again, that photosynthetic process, the oxygen is released, the carbon stays in the plant or goes into the soil. So I just want to be really clear, because we're not always saying carbon dioxide equivalent. It's a lot of syllables. We only have so much time. And just to make sure that those definitions were clear across all their different, as that carbon is moving through the different phases of the cycle, that the language was clear on what we're defining here. So Chris and I sort of collaborated on this part of his study, in which we then took those buildings and modeled them through dynamic hourly simulation to get an understanding of what the operational carbon emissions are for that single unit building and for that 8-unit building. And we looked at that modeling both under the code compliant, sort of code minimum version, as well as the net zero sort of high performance version. And we looked at that with a few different fuel types, and we actually looked at it under a couple of different grid conditions. So I'm going to spin you really quick, and we've looked at the embodied carbon side of things. We want to put that in some context of what does that look like when you factor in the operational carbon as well. So again, we made a bunch of assumptions around the building and its operation. We can, for those of you that really like drilling into the details, we can talk later. Happy to geek out on that. So again, we're starting on these 4 buildings. The red is the high emissions profile of materials, down to the green being the superstoring assembly. And on the left, again, we've got the code minimum, and on the right, we've got the high performance version. We're looking at natural gas heating, high performance, high efficiency gas boiler in Boston, Massachusetts. And we looked at the total emissions during the operational phase of that building between now and 2050. And we gated 2050 as the time window of our analysis, because that's the time by which the IPCC says that our industry has to be net zero carbon. So if we haven't hit these goals within the next 30 years, then we have a very different conversation in front of us. So that code minimum building within that 30-year window is emitting about 10 tons per year in operational emissions. And that's a combination of gas heating as well as the electric loads for domestic hot water and lighting and plug loads, et cetera, et cetera. And so you add that same amount for each of those building enclosure types. We kept the interior square footage fixed, and so it's just the enclosure that's changing outside the interior, and so that same, no matter how we're building, what materials we're using to build it, the operational energy is kept consistent. And then we looked at that for the high-performance unit and added that 30 years of operational energy for the high-performance version of those same 4 typologies. And this is for the 8-unit building, for the big building we're looking at right now. So there's a couple of interesting points to pull out here. We reduced 60 tons of emissions by moving from the code-compliant to the high-performance version of that building over that 30-year period of time, which is fantastic. What's also notable is that every time we make a step down from a higher emission package of materials to a slightly better, to the best that's easiest, to the most optimal, every one of those steps is significantly larger than the amount of operational savings that was realized in a 30-year window by improving the efficiency of the enclosure. Now, do not get me wrong. We are not suggesting that we don't need to worry about energy efficiency. We absolutely need to be building the high-performance building shells. That is a critical baseline. But what we're saying is that there are even larger realizations of emissions that we can actualize by attending to the materiality of how we created that high-performance shell. And that can be significantly larger than just the operational savings. Again, when we're not looking at an 80-year lifespan of a building, we have 30 years within which to try to hit these goals that have been set up by the global scientific community. What's really alarming is that how hard the law of the impact of unintended consequences can hit us when we're not paying attention. And what was alarming was to find that it is quite plausible to build a high-performance building that is significantly worse for the atmosphere than a code minimum building if we're not paying attention to the impact of the materials that we're using to get there. And that is a very sobering reality for those of us that have been in this industry for a really long time and who have been dedicating our lives and our careers to improving our practice and focusing on this very specific goal of improving the operational performance of our buildings. And what we now need to invite ourselves and each other into doing is to figuring out how we can stand on the shoulders of the giants that have created the amazing achievements in reduced operational energy that we as an industry have been experiencing over the course of the last generation or two. And then go even further and bring materials into our point of analysis and use that as an additional leverage point to draw down our emissions profiles. So now we take that same building, we move it off of natural gas, and we put it onto all heat-pumped, air source heat pumps for heating and cooling, all electric building in Boston. And so now we see a drop, which is great. That's exactly what we would expect. That's the whole idea of strategic electrification and high-performance heat pump-driven heating and cooling. And so you can see that little red line above is where we were with natural gas, and now we see where we are when we move over to the heat pump for heating and cooling. It's worth noting that it is not getting to this true net zero environment, even on the high performance side of things, and no small part of that has to do with the carbon intensity of the ISO New England grid. This is where we have to stop just looking at energy as our metric and look at the true carbon impact. And if you're only measuring energy on site, there is a whole host of additional emissions and externalities that are not part of that equation. So a net zero energy building does not mean a net zero carbon emission building. When you look at the full span of emissions that come from delivering all of that electricity to the site and the carbon emission profile of a not super clean grid, that's where we start realizing that some of those true carbon savings aren't materializing the way that we might like to see. When we take that building and move it into a clean grid like Ontario, now we see a tremendous change in the carbon emissions profile of our buildings. We have not changed the energy consumption. We've just changed the carbon impact of using that energy by virtue of how that electricity is produced. And as Chris mentioned, Ontario making a strategic switch from coal generation to hydro generation. Hydro, is that the big truth? Hydronuclear?
Hydronuclear.
Yep. Yeah. We see a tremendous drop in the emissions profile. Now, we can have a very long conversation about all the emissions that come from hydroelectric production that are not showing up here. And there is a whole lot further that we need to go as an industry to have true daylighting and true understanding of what the emissions profiles of different forms of renewable energy generation are so that we can really balance this equation correctly. But with the data that we have available to us, we see some really tremendous changes. And the moral of the story being that, oh, we don't need to think about efficiency as long as we're on a clean grid and build with straw. No, it is all of these steps working in concert together as a system. Better materials, high-performance buildings, and a decarbonized grid. That is what it's going to take to move the entire industry to our goals of true net zero reduction by 2050. And here's some arrows to, make sure you really understand what I'm talking about.
So what we're really going to ask, I think, everyone to do is to take the EUI that many of us really are familiar with and upgrade that to CUI, carbon use intensity. So including those upfront carbon emissions alongside our operational and the externalities of the building impacts. So this is a big shift that I think our community is completely prepared and capable of doing. We just need everybody to work on this. So to meet those emission reduction targets, essentially what we're looking at, as Jacob mentioned, is the 0 kilograms embodied carbon per meter squared by 2050. So if we're going to do that, we need to also include storage. So as we've been saying really clearly, got to deal with the emissions side of things, super important. We have to keep doing that and get better at it. But we also have to include storage in the equation. Otherwise, we are not going to hit that target. So it's really critical. Returning to our sort of Earth system kind of look, this gives us just a really good look at what happens with that CUI if we do business as usual. So the red on the left is if we sort of do nothing and just continue as we're going. And on the right, we can see the potential that our community has to really contribute significantly to our global fate, as people and as this planet. So that was our vision. And so if that was our vision, this is our strategic plan, because you need both, right? You can't just say, we want to be in this place. We also have to say, how are we going to get there? What do you mean? How is that going to be done? So starting again with the red bar and thinking about that building that Chris presented with all of the particular materials that were a part of that, we have to stop doing that right now. So anyone who's got that on their drawing board, in their plans, in their estimate, I would challenge everyone to see how that you can pivot from that place now. Within 2 to 3 years, I think this community can really make the norm doing that more moderate carbon building. So materials that are available right now, Chris mentioned Home Depot, but many of our locally owned building supply is a great source as well. So we're talking about those materials that are available that we just have to remember to use and remember to spec instead of those high emitting materials. So that's your local woods, your celluloses, anything plant-based, and moving away from the higher intensity materials. The 3 to 5 year goal, getting to that 0 carbon. So again, getting even a little bit further with what we're doing with the materials. And then the carbon storing building being within 5 to 10 years. So this is a big challenge, right? I know all of you out there who have your practices are your minds are churning. How is this going to work? So we hope to show a couple of case studies and some examples that can point the way forward for how we're going to do this. So again, that carbon use intensity actually now becoming our collective new definition of what a high performance building is.
All right, so it's challenging to try and think about this whole list of different things and try to get some sense of prioritization and order and figuring out where we sort of step into the work. And I want to give credit to Danella Meadows, who's a brilliant systems thinker and Vermonter, who came up with this wonderful framework of how to change a system, how to change a paradigm. She has this great paper, Leverage Points, Places to Intervene in a System, and identified there's a whole series of different points of intervention, from very simple, sort of like rudimentary, sort of definitional points of intervention, all the way up to changing changing the entire paradigm in which the system operates. And those different leverage points will have different impacts on how rapidly a system can move and change. And that's what we're talking about. We're trying to invite the opportunity for us to redefine and to recreate the paradigm in which construction is achieved in this environment. So riffing off of her identification of how you can identify these leverage points, we want to just use that as a framework. So starting with just counting carbon, getting used to understanding the impact that we're having and starting to pay attention to what those numbers are. That is something that we can immediately start doing without having to even change our material practice. So we'll just gain greater awareness. That'd be the first point of leverage, is just to understand the impact that we're having. And we all have, us included, a lot of work to do to really understand what these carbon numbers mean. Moving up there, we can just start using lower carbon embodied carbon materials on our next projects and just make some of those simple material switches. Then actually changing the architectural engineering and construction practices to reducing carbon emissions as an overall goal, moving beyond just swapping out a given material to setting some goals around emission reduction. And then the next step up for that would be to actually design as if we are optimizing carbon storage. So instead of mitigating the impact, optimizing the potential of how we could design and construct and engineer our buildings to be carbon storage. So those are some of those first steps along the leverage point.
And one of the really interesting things that came out of the study I did was that this very first intervention, the sort of simple substitution of materials, so the global warming potential of those materials was better, but what was really interesting was that on all the other 6 areas that an environmental product declaration looks at, the material with the lowest global warming potential in its category also had the lowest impacts in all of these other categories. So by doing this one sort of good and right thing, I just happened to do the good and right thing in a whole bunch of other areas without having to really know that or have that be motivating me. And the other thing that came out of it is that none of the best materials in their category had any red list chemicals. So I'm going to be making a healthier building for my building occupant by making that sort of climate-friendly choice. And at the end of life, most of those materials are recyclable or biodegradable, and they also don't have the weird chemicals in them, so they also sort of lighten the load at the end of the building's lifespan. So this simple substitution, while it's sort of at the early stages of the leverage of changing the whole system, has a range of really important impacts that it sort of just carries along with it, that are sales points for us to be talking to clients about, and sort of meaningful to people for whom maybe carbon isn't the most meaningful part of their reason for wanting to make a building.
All right, the retrofit world is a really important space to be addressing this. A lot of folks are thinking that we're just talking about new construction, but we're incredibly proud of the work that we've been able to do with new frameworks in partnership with Efficiency Vermont and the EEN network, doing really wonderful weatherization work. And this is an incredible community of folks committed to retrofitting this very old housing stock in our region. So we took some projects that we'd run through HERO, the reporting program for the Home Performance and Energy Star program, and just did a look at some projects we'd done with spray foam and with cellulose insulation as bracketing the 2 sides on a given band joist measure. And we found that we did the jobs that we've done with cellulose. We start by storing, bracketing this. So this is just a sort of preliminary look at some of this data and how, what the impacts are of the material choice against the operational savings. And we're really excited in this upcoming year to be partnering new frameworks, partnering with Vermont Integrated Architecture and Efficiency Vermont through their R&D program to be sponsoring a study to be looking more closely at what are the impacts of material choice within the weatherization program and for the retrofit work that we're doing here in Vermont, to make sure that as that program expands and that critically important work that we're doing to improve the operational efficiency of our housing stock, that we're not creating more damage or unnecessary climate impact in the process by not understanding what the impacts of materials are, and bringing that focus of materials into the retrofit and weatherization practice as well. So look ahead for that, and my gratitude to Efficiency Vermont for taking this issue seriously and helping to support that analysis.
And I think I wanted to point out too, just since we're talking about affordability in this conference as well, up on the upper right, we've got our numbers there for doing those measures with cellulose and caulk versus the spray foam and intumescent paint for that band joist condition. And so retrofit impacts, again, this is also within our company. So this was internal research that we're doing on our measuring our own impacts of our work. Looking at a closed cavity roof insulation condition, again, a project 945 square feet brought to R49 here in Burlington. And on the left, I'm going to point to the right this time. On the left, there's this grouped system here where you see the cellulose embodied carbon is the dark blue. The next bar is that operational carbon, and then the net is to the right of that. So that shows the net impact of that measure. And then here's that same exact R value, that same exact condition done with that spray polyurethane foam and where we get with the net. So for us, this was just really helpful to be able to look at our own practice and say, does this really matter? And this shows us that it does. It's important to look at. Right.
And for a net savings in cost to implement the measure.
Yeah, and again, the costs up there on the right as well, because we're trying to really, again, the charge of like, well, isn't this more expensive, and is this actually possible? It's, for us, this is showing that it really is. All right, case studies.
Sure, which I'm going to fly through really quickly because we're starting to dwindle on time, but just wanted to show you that again, this is doable and it is affordable. So this is a building that we did, a little house that we did with our school up in Ontario. So fairly small, about 1,100 square feet. But the thing I sort of want to draw your attention to is that the little bar that says that it's storing 250 kilograms of CO2 per meter squared. That's better than double the best case scenario that was in my study. And this is a real building that we really built for the same cost that other people can build buildings for. And as a plant-based building, it doesn't look like a hippie shack. So, what we're saying
pretty critical.
Is that not that you have to use all plant-based materials, you have to use enough plant-based materials to offset the other things. If you want metal siding, you can have metal siding. If you need a concrete foundation, you can have a concrete foundation. It's not a 100% plant-based building. It's make sure that your plants are basically offsetting your emitting materials to the degree that you've set a target for. In this case, we set a target to store a ton of carbon. You could set it to balance out to 0. You could set it to, be 50, kilograms per meter squared, or, whatever the target is. It's not that you have to drop everything and only use plants. You can build the building you want to build and be smart about choosing a range of materials that'll get you there. And this is a building that isn't anything that I did. This is in France, but this is taking this notion of a carbon storing building to a larger scale. So it's a 7-story apartment building built with mass timber and prefab straw bale wall enclosures on the outside. And it's storing about 8 times what the best model in my study showed. So they're storing 814 kilograms per meter squared. And so this is, taking the results and showing that you could both scale it in size and scale it in impact, and that it's doable now. This isn't sort of dreamy, future stuff.
All right, so moving towards the end here, now we're starting to look at these larger points of leverage and the real potential for paradigm change when we start looking at how we can move into our supply chain. So it starts with just handprinting and really broadcasting the successes that we've had. And that's what we're doing right now. I feel incredibly honored and blessed to be able to share some of the successes that we've been able to realize in our practice and highlight those in others' practices to help inspire and shine some potential of what we as an industry can do. Changes in codes and programs and policies. Again, big credit to Efficiency Vermont for taking this seriously and starting to look at this. And there's a host of other programs and policy developments that can leverage significant change across our industry. Changing the culture of our industry, and that's both in all ways, in all manners necessary to create a holistic change. And then seeing this industry collaborate with our partner industries in manufacturing and agriculture and forestry, et cetera, et cetera. Once we start getting to those levels of impact, we start recognizing our place within a global climate movement, where across all industries and across all regions, we're able to caretake the ecosystem health of our planet. And just, in case you didn't get the first time.
Now they're all there. All
So we looked at Project Drawdown. Again, this, if you're not familiar with it, take a look when you've got a few minutes. And we looked at what are the impacts that they've highlighted as the primary points of intervention within the building world, the AEC kind of like space. They found about 143 gigatons could be realized by optimizing all of those points of intervention. But we're talking about looking at our supply chain as well, and really talking about how do we bring the way those materials are created. And we start looking at all the different points of intervention that exist within a biogenic supply chain, sustainable supply chain for materials, and we can almost double that impact. And many of those items are way higher up in the impact category than a lot of those building level interventions. And so this just realizes the potential we have when we can start opening our eyes and our arms beyond just the building itself to where those materials come from. And a few really quick case studies around that. Improved rice cultivation, number 24 in the top 100 things we could possibly do to draw down carbon from the planet. The roots of the straw bale building movement back in the 80s came from exactly this relationship where straw was diverted from being burnt in the fields in California to being put into building insulation across the southwestern United States. Now there's a new plant that just opened up last month adjacent to a California rice field that is diverting straw that is otherwise being flooded using very precious water resources and anaerobically decomposing straw to create really high emission methane. That is now being diverted to create straw-based MDF board that can be used in a host of different applications across different products in a building. So this type of inter-industry collaboration is exactly the type of whole systems approach that can leverage significant change when we look beyond just the fact that it's an MDF board. And we can bring that right home here in New England, where we have a critical need to be able to invest in our regional wood purveyors. We've seen mills closing regularly over the course of the last decade. And what we lose in that is really significant. The potential of being able to reinvest into our regional land-based economies and industries is critical, not just to be able to create climate responsive and healthy rural economies and looking at this from a jobs creation and economic development perspective, but urban centers require healthy and vibrant rural economies to create the food and materials that those increasingly urbanized American centers need to be able to function. They're not growing all those trees and all that food within that urban complex. So we need a harmonization of urban and rural economies to be able to realize these goals for our entire region. And the opportunities that we have within Vermont and within the New England region to be able to optimize the potential of creating a working landscapes model for conservation and avoiding land use transfer and fragmented land management practices is incredible. We have the real opportunity here to integrate those systems to be leaders in our nation around how we can optimize our natural resources, both within our industry and beyond.
Okay. So quickly, codes and policies that are starting to steer in this direction. In case you think the three of us on stage are the only people thinking about this, the World Green Building Council, just at the end of last year, came out with a call for 40% embodied carbon reductions by 2050 that was signed on to by some of the biggest corporations on the planet, most of the green building councils around the world. So there's a lot of action actually starting to happen at that level. If you want to be able to sort of measure and verify some of this stuff in your own projects, the ILFI Zero Carbon Certification Program is a tool for doing that. It counts both the embodied and the operational carbon, and same with the Canada Green Building Council's Zero Carbon Building Standard. And then this is really exciting, and you're the first people to know about this anywhere, but up in my home area, a group of municipalities up there have gotten together with myself to come up with an incentive program, and later this year, builders are going to be able to get $10,000 back on a building if it meets a certain carbon threshold. So these are the kinds of things that will start to steer that forward and push that forward. And it's really exciting to see more and more of that starting to happen.
Yeah, so as we were talking about earlier as well, I mean, because this is a systemic approach that we're going to look at, climate justice and really reversing climate crisis is integrated with social justice and with people working in a just way with one another, in addition to being in right relationship and just relationship with planetary systems. So for us, this is an integrated thing. It's a problem that is a social problem, and addressing those things in tandem are going to get us to the holistic solutions that we need. So you see here the Green New Deal, looking at ways to leverage our social systems and our political systems to be able to build these things into reality now. We really need them soon, and we need them now. And we need everyone to be uplifted and brought along by this. So climate crisis is real, it is upon us, and we do not need permission. We need bold action and conviction to make these radical changes in our practice. So the word radical, I don't know if everybody knows, but it means going to the root, which I sort of love given what we were all talking about in terms of the roots of the plant and fixing carbon in the soil and that being critical. So we really are asking each and every person here to go to the root of the work that you're doing and to bring into it this kind of both complicated and simple answer at the same time, which is, I think, really what we're saying. And that by doing that, by taking this immediate action, we can actually, in this room, become climate heroes. I don't know how everyone else feels, but waking up in the morning and feeling like, wow, just being a human being, I'm messing everything up. Through my work, everything is about emissions and how do I minimize it, and I'm doing a terrible job. It's a bad feeling. What is wonderful about this work is that it shows us that if we actually work in partnership with natural systems and are intelligent about the way that we understand our work, we actually can be a benefit to the planet that we're on and to each other. So that is the potential here that we're really putting out there. This is inspiring and exciting, and again, puts us in the driver's seat of making these changes. So we're going to wrap. We're going to leave you with build with plants that build soil and rocks made from the sky. We didn't talk about that one too much, but we will later.
We need to fix what we have, so the whole notion of all the retrofit work that's going on here is absolutely critical, the work that everybody's doing to help those existing buildings and to bring the carbon piece along with it.
We really need to focus on where materials come from and how we get them.
We have to do what we can with the current technologies, and we have to make better technologies.
We need to change the codes and educate everybody and do it quickly.
We need to learn how to count carbon, both on the material side and on the operational side, and get some sense and scale of what those numbers mean and learn how to set appropriate targets for ourselves.
We need to build relationships of mutual aid with people beyond profit.
We need to build understanding of and relationships with the ecological cycles.
And we need to act with great urgency and tremendous passion and abundant joy, because this work is really hard, and we need each other in the struggle together, and we need to do it with a song in our hearts, because we've got a long way to go, and that's the way we're going to get there, together in joy. Thank you so much.
Thank you. Who wants a photo?
All right. We're going to get the photo.
So there's a reception on the trade floor for a few minutes here before the next session starts. Keep your eyes out for all the good carbon counting and carbon intervention sessions the next 2 days, and have a wonderful conference.
Thank you, everybody.